Hi, welcome back to Calculus. Today, section 2.3. Today we get the precise definition of a limit. So it's not going to be on this first board. It's going to take us just a little bit of time to get to it. Not too much. It'll be on the next board. So what we want to look at is the precise and exact mathematical definition of what it means to have a limit. We've kind of waved our hands at it a little bit. We've said, hey, we want to know that if we get close enough to this x value, that we get close enough to a y value, right? We're trying to squeeze in on some y value that we're calling a limit for a function. But that's not very precise. It's not rigorous. So we need a way to rigorously determine limits. And so here we go. The precise definition of a limit. All right, so we're going to get started here with an example, and we're going to kind of walk through this, and it's going to actually really lead us into the precise definition. And then we'll look at the precise definition, and then we'll have all sorts of fun. So let's look at this example. The example is y is equal to x plus 4, or you could call it f of x is equal to x plus 4, and we want it to be near x equals 2. So we're going to be looking at the limit as we go to x equals 2. As you can see, I've made a graph. It's just a line, right? It's a line with a y-intercept of 4. And it really looks like if you get close to x equals 2, that the graph gets really close to 6. And that makes sense, right? It fits with all the limit rules that we learned in the last section. And quite honestly, it's just, it's pretty obvious, right? We know what happens when x is 2. We get 6 here. So here's how we will go about this as we get into this more rigorous definition of a limit. So we want to ask this question. How close to 2 must x be to be within 1 unit of the limit of 6? So this is not quite the precise definition. Remember, we want to be able to get as close as we possibly can to that limit. That's the arbitrariness that we looked at in the previous sections. But here we're going to say, okay, well, how close would we have to be to, get within 1 unit? To have y values that are only 1 off of that limit. So what that means is we want the distance between y, the y value, and the limit to be less than 1 unit, right? We want to be within 1 unit. And so when we take the absolute value of a subtraction problem, what we're really talking about here is the distance between y and 6. So we set that up. But then we know what y is equal to. Y is equal to x plus 4. So we can replace the y with x plus 4. You can clean that up. 4 and negative 6 makes minus 2. And so here we can actually see it again. Now we have the distance between our x value and the x value we want of 2. Okay, between other x values and the x value that we want to be approaching of 2. And we can see that we have to be within 1 unit. So we started with how close we wanted to be to y, and we rearranged it to see how close we wanted to be to x. In this case, it's also 1 unit. Another way to think of that is we could rewrite this absolute value inequality as negative 1 is less than x minus 2 is less than 1. Basically, x minus 1 is sandwiched in between negative 1 and positive 1. And then if you solve that for x, that means that the x values that we work are actually the numbers between 1 and 3. Right? And that makes sense. That gets us very close to the x value 2 within 1 unit. And if you plug in 1, you get 5. That's within 1 unit of our limit of 6. And so there you go. And that's basically the process that we're going to go through. We're going to make it a little more generic. It'll be way more fun. So hang on, let me get another board. All right, so here we are with the precise definition of a limit. You can see this on page 70 in your book. So if you have any trouble reading what's on my tiny little board through the video screen, feel free to go into your book to page 70 and look at this. Basically, it's going to be similar to what we just did with that last example. With that last example, we said, hey, what would it take to get within 1 unit of the limit that we think exists? And then we were able to find a number, which also happened to be 1, that if we were within 1 unit of x, then we were close enough to be within 1 unit of y. Right? That was kind of what we did on that last one. So the definition is going to take that and it's going to make it just a little more generic. And we're going to see some weird notation here that you're probably not used to, but that's okay. You're going to get used to it. So here we go. says let f of x be defined on an open interval about x equal to c, except possibly at c. So again, we have this number there where we're going to try and take the limit. That's the c. And the function is defined around that number. Remember, it doesn't have to be defined everywhere, just kind of close to c. We say that the limit of f of x as x approaches c is the number L. We write the limit as x approaches c of f of x is equal to L. If, this is a huge definition, very important definition in mathematics, if for every number epsilon, so this is a little Greek letter, greater than 0, basically it's an arbitrarily small number. On that example we just did, we used 1, right? We wanted to be within 1 unit of the limit. Now we want to be within some arbitrarily small number. For any number we pick, there exists a number delta, there's another Greek letter, that's also greater than 0, such that for all x, if x is, if the distance between x and c is less than delta, right, that's that absolute value notation again, that implies that the distance between the function and the limit is less than epsilon. So we're going to do kind of the same process, except now we're going to use epsilons and deltas. And so this will be fun. No, not really. Honestly, most people don't like this kind of stuff. It's a little weird, it's a little strange. Hopefully you get used to it. It's really not that bad, but you'll see some kind of goofy stuff too. So let me get a new board and we're going to start doing some examples. Some of the examples will go with this definition, we'll use epsilons and deltas. Some of the examples will make a little bit more like that first one we did, and we'll actually work with some numbers. And yeah, some of it's going to be just a little bit weird. So here we go. All right, I was wrong. One more thing before we look at some examples. Here's kind of a picture of what's happening. Again, I think you can probably find this in your book, somewhere around page 70. Let's see, I'm kind of looking. Yeah, there's some real nice pictures of this on page 71 in your book. So what we have is we have the number we're trying to approach, c, and we have the limit that we think, or what is claimed to be the limit. So the idea is, here's my limit plus epsilon and limit minus epsilon. That's that very small number. It's arbitrarily small. And what we're saying is if we're this close to L, how close do we have to be to C to force ourselves in there? Okay. Now, it's very important. You have to be able to find some little piece around C where you get trapped, okay, in that little space around the limit. If your function cannot be trapped, okay, think like a sine curve. There's some really weird stuff that happens with sine curves if you do it right. They go up and down, and so you can force them to continue to go up and down no matter, anyway. So you have to get trapped in this little tiny rectangle here. Okay, you have to be able to find a interval around C where you're stuck in that little interval around the limit. All right, now we'll do some examples. All right, so here's our first example using epsilons and deltas. Again, we can do this either with actual numbers for epsilon to start with, like our very first example that we did at the start of the section, or we can do it with the more just generic, unknown quantities of just epsilon and delta. So I want to show that the limit as x approaches 3 of negative 2x plus 1 is equal to negative 5. Right, and so from the limit laws that we learned before, we know that that's true because we can just take 3, we can plug it in, and we get negative 5. But we want to use our precise definition and start to just kind of get this idea of we're squishing stuff in. So here my C is 3 and my L is negative 5. And I'm going to set this up using that very precise definition. I'm going to start with what we want. We want to end up with the distance between the function and negative 5 being less than this arbitrary epsilon. Okay, because in this case it's arbitrary. We don't know what it is. It can be as small as we might possibly want. So I then replace f of x with the negative 2x plus 1, and minus a negative 5 gives me a plus 5. I combine some like terms, and I get the absolute value of negative 2x plus 6 is less than epsilon. Now, that's not really the form that we want. You can look ahead here and see down here that I end up with the absolute value of x minus 3 less than epsilon over 2. But this is the form that we want this absolute value to be in, because this says the distance between x and 3. And so that's where we're trying to get to, right? Because that's our C. So keep that in mind. We really want to, we're here, and we really want to get down here at this x minus 3. So the thing that I notice first is I have a negative 2 on the x. I don't want that there. So I factor out the negative 2. That gives me the absolute value of negative 2 times x minus 3. If you split an absolute value across a product, you just take the absolute value of both parts. So the absolute value of negative 2 is a positive 2. So we have 2 absolute value of x minus 3 is less than epsilon, and we just divide both sides by 2. So if the distance between x and 3 is less than epsilon over 2, and that's what we're going to call our delta, then you can take all of this back, and the algebra works in the reverse order, and gets us to where we have to be with the limit. And there we go. That's how we can use this precise definition of the limit. Technically, it runs from bottom to top. Okay, so usually we start here and work our way down to find that delta. And if you really want to do this very, very accurately, you turn it around then for your answer. You start here, you say, hey, let delta be equal to epsilon over 2. And then you say, okay, if you're this close, because that's the definition, we start here, and then you work it up that way. But if you do this and find the delta that works, I'll be happy. So, all right, let's try another example. Okay, our next example. So on this one, we have, for the limit is x approaches 7 of the square root of x minus 3 equal to 2. We're asked to find a delta greater than 0 that works when epsilon is 1. So this time we have a specific number. Remember, we have these two different kinds. We have the generic case when epsilon is just some unknown arbitrarily small number, and we have the case where we have a number for epsilon. So in this case, we have a number. We have 1. So again, I want to start with that distance between my function and the limit. So in this case, my function is the square root of x minus 3. And so I set it less than 1 because that was my epsilon. Now, unfortunately, this one's a little bit different. I can't really rearrange this. Remember, I would need to get down to an absolute value of x minus 7. There is nothing here that looks like an absolute value of x minus 7, right? There's nothing remotely along those lines. Really, basically, if it's not linear, if it's not like that last example we did, you're going to have to do some weirder stuff. So let's see what we have to do on this one. Well, for starters, I'm going to get rid of the absolute values. I know that the absolute value being less than 1 means that the stuff on the inside has to be sandwiched in between negative 1 and positive 1. Once I have that, then all I'm going to do now is I'm just going to solve it for x. I'm going to find the x values that would work, and then we'll figure out what that delta has to be. So I add 2 to both sides, and then I square both sides, and finally I add 3 to both sides. So we end up with x being sandwiched between 4 and 12. And that's great, right? It's good because where are we trying to take the limit? At 7. 7 is in between 4 and 12, so that's a good start. If 7 weren't in there, we'd have a really big problem. All right, but 7 is in there. So we have found an interval with x values that works. However, delta, remember, is going to be equidistant on both sides of 7. And as you can see on my number line, 7 is not, I didn't draw it very accurately, but 7 is not right smack in the middle of this interval. In fact, if you subtract to find the distance from our c value to each of the endpoints, 12 minus 7 gives us 5, and 7 minus 4 gives us 3. We need the smaller one because we can't use this whole interval because remember, we want this the interval we're looking for with delta. The interval we're looking for with delta is going to be equidistant. It's going to be the same distance on both sides of 7. And so we need the smaller of the two. And that's just going to be something that we have to do sometimes. You get to the end of this one, you've got an interval where everything works, but it's not symmetrical around our c value. So we just make it symmetrical. We're going to let delta be 3. And so now if we keep everything from, I guess it'd be between 4 and 10, then we have our interval. But the delta that we get for the epsilon we started with in this case is 3. So there you go. I have some more examples, but they're going to be in the next video. So hang on.